Welcome everyone, and thank you for joining. In this presentation, we are going to look at signal and power integrity design and verification with hyperlinks. Hyperlinks is an integrated family of products for high-speed system design, automated optimization, and verification. By design, we mean all the planning and analysis that you do before layout to define the rules you want to use to place and route the board. By optimization, we mean using automated tools to improve design performance for a metric of interest. Traditional methods of optimization include iterative analysis to improve your design, but that often takes too long. We'll look at how hyperlinks can help you improve design performance automatically. By verification, we mean post-layout analysis, or what you do once the board is routed, to determine that the design is ready to release to fabrication. There are three main design application areas for hyperlinks: DDR interface design and verification, serial link design and verification, and general purpose signal and power integrity, which overlap with some of the capabilities we'll discuss here. Hyperlink's products include Hyperlink Schematic Analysis, which automates parametric checks, eliminating the necessity to manually review complex schematics. Hyperlink's AMS, a powerful circuit simulator for analyzing complex analog and mixed signal designs. Hyperlink's DRC, which provides fast, rules-based design checking of PCB layouts. Hyperlink's DRC can identify layout issues in a fraction of the time that simulation requires, and screening designs with DRC before investing in detailed modeling and simulation will help speed up your design cycle. Hyperlink's advanced solvers, which provide accurate 3D electromagnetic modeling of PCB structures and are seamlessly integrated with Hyperlink's SI and PI to provide complete front-to-back analysis flows. Hyperlink's SI and PI, which share a common user interface. Hyperlink's SI performs signal integrity analysis of DDR interfaces, SerDes-based serial channels, and general-purpose high-speed design. Hyperlink's PI performs DC and AC analysis of PCB power delivery networks, or PDNs. Hyperlinks is tightly integrated into Siemens' family of PCB design capture and layout tools. Design is an iterative process. As you lay out the board, analysis is used during the physical design cycle to help you tune and improve the design in real time, rather than waiting until the layout is complete when it's too late to make substantial changes. Combining hyperlinks with Siemens design capture and layout can significantly reduce your design cycle and improve your design's performance. In addition to offering superior integration with Siemens PCB tools, Hyperlinks is also the most widely interfaced signal and power integrity tool on the planet. With Hyperlinks, you'll have the widest range of PCB import capabilities available. Now, let's talk about general SI-PI pre-layout design analysis. Hyperlinks has established a flow for pre-layout exploration that guides the user in developing design parameters. Starting with stack-up design, Hyperlinks allows users to import and test different stack-ups to see the effects on the design. From there, we move to trace and via design. Here, the user investigates trade-offs in routing and via parameters that affect the desired characteristic impedance. And then moving to topology exploration, where the user can explore different routing topologies, termination schemes, and crosstalk. This is an iterative process. As with all testing and simulation, you normally aren't done after the first run, and the tool can store results for comparison from multiple simulations. Moving to power integrity, we start with DC design. For most users, performing any power integrity analysis is more optimally done once the components have been placed. Same with AC design. This would be done mid-layout, but can still help prevent respin if performed before completely routing the board. This accumulates into a set of rules you use to place and route the board. Let's take a closer look at each one of these sections. Hyperlinks helps users develop a stackup that accurately represents what they'll get from the manufacturer. Within Hyperlinks, you can design around a characteristic impedance and see what changes affect your ZO on a per-layer basis. You can include manufacturer options like surface roughness and trapezoidal traces for more accuracy. Hyperlinks includes an extensive list of options and customizations for the user to explore realistic stack-up design. Siemens EDA does offer a dedicated stack of design tool that easily integrates with hyperlinks. zPlanner has an extensive library of materials and options created from collaboration with manufacturers so that the user can be confident they are designing something they can actually build. Additionally, Hyperlinks supports multiple stackups for multi-board and rigid flex projects. DC analysis is something that will most likely be performed once the components have been laid out and will help identify power issues earlier in the design process before fully routing the board. Hyperlinks assists users in exploring trade-offs in component placement, stitching vias, and power plane strategies. Users can simulate DC voltage at component power pins, plane and via currents, power loss, max power density, as well as point-to-point resistances. Additionally, Hyperlinks can export power planes from a post-layout design and perform what-if simulations. Now let's look at AC analysis. Hyperlinks can perform multiple analysis to aid in the decoupling strategy to meet design requirements. Analysis can vary in accuracy and speed depending on the user's needs. AC analysis can generate Z-parameter plots for each power net of interest to ensure the design is meeting the desired target impedance profile. Simple lumped analysis is available for quick exploration of the mounting effectiveness of the decoupling capacitors and runs very quickly. More advanced distributed analysis can capture the detailed effects necessary to see how spreading inductance and capacitor mounting locations affect the performance. Optimization of capacitor values and footprints can be achieved by using the decoupling optimization wizard. The wizard intelligently investigates trade-offs in cost and performance by iterating through the decoupling values and available footprints to minimize the impedance against a target. Additionally, the new integrated solver significantly speeds up solve times while minimizing memory consumption, even when tackling large designs that competing solvers can't analyze. Hyperlinks can export your results in an HTML or CSV file for easier reporting. In pre-layout exploration, you can identify various parameters to achieve the desired ZO or characteristic impedance. You can explore how via parameters such as anti-pad shapes and stitching vias play a part in the overall design of the channel. The designer can explore trade-offs in trace width and stack-up materials to determine many things like single-ended and differential impedance in parasitics. Starting off with simple simulations will give you a general idea of how your design will perform. From there, you can increase accuracy on constrained parts of your designs. S-parameter models can be created and exported to capture more complex behavior. One of the more critical items to explore in pre-layout is how routing topologies affect signal integrity and timing. For example, you can see the effect of drive strength, termination impedance, and trace length affect your design margins. Crosstalk and routing density trade-offs can easily be investigated, allowing the designer to mock up different scenarios and make changes accordingly. Additional trade-offs and manufacturing effects can be explored as well, such as backdrilling, surface roughness, and realistic etch factors. After finishing simulations, you should have a list of design parameters and constraints that can be used to place and route the board. Here, the goal is to document all the important aspects of simulation and ensure that the board is routed with those constraints so that performance can be realized in post-layout. This wraps up the pre-layout section of the presentation in the Hyperlinks flow. Now let's talk about design optimization. The first example of optimization is swept parameter analysis. Swept parameter analysis gives users the ability to test multiple scenarios and view the results by iterating through all permutations. Each scenario can be overlaid on the same waveform viewer for easy visual inspection and comparison. A perfect example of this analysis would be to investigate trade-offs in termination values or trace routing length, for example. Listed here are just a few of the many variables and design aspects that can be swept to find optimal values for your design. As mentioned earlier, the PDN decoupling optimizer intelligently selects capacitors while working within the existing footprint constraints. It elevates multiple capacitor models from your component library and can identify unnecessary mounting locations to reduce the BOM cost. What's particularly exciting is the seamless integration between Hyper-PI and the PDN decoupling optimizer. This integration, combined with improved capacity for complex multi-layer PCB designs, means you can efficiently analyze large port count PDNs and quickly iterate through hundreds of design alternatives to find the optimal solution. Next, we're going to talk about post-layout verification. Just like in pre-layout, Hyperlinks has established post-layout verification flow that makes it easy for users to follow. In post-layout, we start with electrical rules check. Hyperlinks automates much of the visual inspection done by an engineer and produces reports based on rules set in Hyperlinks DRC. For power integrity, users can verify that their designs meet both AC and DC design requirements. Here, users can perform full power integrity verification on their routed board to see how well their PDN performs. Next, we move to batch simulation. Hyperlinks supports the simulation of multiple nets or even entire boards if necessary, with specific wizards designed to analyze complicated interfaces like DDR and SerDes. With high-level verification of your board done, interactive simulation enables the user to take a deeper dive into problematic nets and diagnose issues. Progressive accuracy is the trade-off between accuracy and simulation time. As we achieve more real-world environments for testing, the time to simulate also increases. Starting off with a simpler simulation can reveal glaring issues in a fraction of the time. All of this culminates in comprehensive results reporting in a pass-fail style, and these reports can be used to make any necessary changes for your design. The first step in the post-layout process is to review the design for errors and verify the constraints have been met. However, manually reviewing a layout can be very time-consuming, tedious, and extremely error-prone. Hyperlinks DRC automates this process, therefore saving a considerable amount of time and alleviating the risk of missing issues through a manual review process. Automated electrical rule checks should be done first to identify issues prior to simulation, thereby finding and fixing simple issues before first tying up valuable simulation resources. Hyperlinks DRC includes over 100 built-in rules that span multiple areas and can be customized to fit the needs of the user. Listed on this page are just some of the checks that Hyperlinks DRC can perform. These rules include high voltage safety, IC packaging, signal integrity, power integrity, and EMI. Additionally, customization enables you to write your own rules to capture unique design requirements. And finally, services are available to help you write those custom rules if needed. Now let's talk about batch simulation capabilities in Hyperlinks. Successfully analyzing a DDR interface involves knowledge from multiple disciplines, including signal integrity, timing analysis, and power integrity, and must satisfy a myriad of design requirements. There are signal quality requirements on individual signals, timing relationships that must be satisfied between groups of signals, and even requirements on the power delivery network. All of these requirements must be met simultaneously and with adequate margin under worst-case conditions for the design to work. We're going to look at how Hyperlinks can help you meet all of these different verification needs. Introducing the Hyperlinks DDRX Batch Wizard. The wizard is an all-inclusive, JEDEC-based guided utility used to analyze entire DDR interfaces for complete signal integrity and timing analysis. The user supplies the schematic or the board files, the IBIS and the timing models, and configures the wizard for analysis. Hyperlinks analyzes the design and produces a comprehensive report with pass-fail status and can show you design margins, waveforms, and even eye diagrams. The wizard can handle DDR through DDR5 and low-power DDR through low-power DDR5. Hyperlinks ships with timing models for the DRAM devices for all protocols and includes a generic controller timing model that can easily be customized for your particular needs through the intuitive controller timing model wizard. The user can quickly assess the effects of crosstalk and power aware, including 3D models of VITAs and S-parameter models for connectors. Additionally, multi-board systems are easily configured to analyze a complete system. Now let's look at the SerDes compliance and batch wizards. Hyperlinks includes a complete integrated solution for compliance and IBIS AMI-based serial link design and verification. The SerDes solution includes pre-layout schematic-based topology exploration to develop placement and routing rules using progressive accuracy and standards compliance analysis. It provides a methodology for PDN design and verification for both DC and AC behavior. We can also investigate how swept parameter analysis can be used to improve design margins, how Hyperlink's design space exploration can be used to explore and optimize designs with very large design spaces, how hyperlinks can ensure your design meets standard protocol requirements using automated compliance analysis. It includes automated post-route extraction and modeling that lets you easily verify the behavior of all your signals, not just a select few. And it also includes comprehensive HTML-based reports that tell you what you want to know the most, what passed, what failed, and by how much. The SerDes Compliance Wizard offers a complete model-free, protocol-based analysis to ensure designs are meeting the complex requirements for today's high-speed serial links. The Compliance Wizard comes with over 400 built-in protocols and variants covering Ethernet, HDMI, JESD, MIPI D-PHY, OIF CEI, PCI Express, USB, and more. The user simply selects the nets for analysis, picks the protocol, and configures the analysis. A comprehensive report yields detailed results for a wealth of time and frequency domain results necessary for designers to make informed decisions on whether the design is compliant. And while the built-in 2D field solver is quick, convenient, and accurate, additional accuracy at the cutting-edge speeds can be achieved by extracting full-wave 3D models for vias. Detection of these 3D areas is automated with a variety of configurable options for ultimate flexibility. Intelligent reuse allows areas to be identified as similar, saving precious computational solving resources. Beyond the Compliance Wizard, the SerDes Batch Wizard supports IBIS AMI models to simulate the detailed equalization schemes of today's high-speed serial channels. Now, let's take a look at Hyperlink's Advanced Solvers. Hyperlink's Advanced Solvers is a complete family of electromagnetic solvers that is fully integrated into the Hyperlink's workflows. This integration includes 3D areas, 3D Explorer, parasitic extraction, and advanced decoupling wizard, and more. Hyperlink's advanced solvers support job distribution for high-performance parallelization. 3D Explorer comes loaded with customizable templates of common structures such as single and differential vias, cables, breakout patterns, and more. Simple swept parameter analysis can be set up to explore trade-offs and quantify design margins. Hyperlink's advanced solvers is comprised of 3 solvers with distinct advantages and disadvantages that can be invoked from within one GUI. The fast 3D solver executes quickly and is used to extract RLGC values for components such as packages and PCBs, including SPICE netlist export capability. The hybrid solver can be used to model loss, coupling, and non-ideal return path and PDN effects for entire PCBs and larger areas. It is fully integrated through automated setup when running Advanced Decoupling Wizard and supports parallelization through job distribution. The full wave solver is used to model the most critical aspects of your design with the highest level of accuracy. It is fully integrated for 3D area solves and can be used in serial channel, DDRX, and general purpose signal integrity analysis. It requires the highest level of computing resources and also supports parallelization through job distribution. Hyperlink's advanced solvers also includes 3D Explorer for efficient experimentation and conducting what-if type simulations. 3D Explorer includes over 25 built-in templates for various structures like BGA breakout patterns, cables, as well as single-ended and differential vias. Through swept parameter analysis, 3D Explorer allows the designer to configure and run a set of experiments to optimize a structure for a particular need. The user simply picks a template, configures the parameters to simulate, and runs the experiments. Reporting is comprehensive and intuitive, allowing the designer to assess trade-offs and pick the best solution. So I mentioned extracting 3D areas earlier in the webinar. Hyperlinks can also extract 3D areas of vias using the full wave solver for additional accuracy for today's high-speed signals. Hyperlinks uses the DRC engine to find the areas on the board that require 3D modeling automatically. The signal and its associated return path, including stitching vias, are fully modeled, and the area boundaries are chosen to ensure TEM flow at the signal ports. Hyperlinks creates the corresponding simulation projects for the full wave solver and solves them automatically without additional intervention from the user. These areas are then ready to be used interactively or in a batch analysis. Now, I would like to talk about multi-board analysis. Multi-board systems, including rigid flex designs, can be analyzed in hyperlinks with ease thanks to an intuitive GUI and integrated connection editor. Hyperlinks offers several ways to model connections between boards, including shorted or non-electrical models, simple RLC, and S-parameter and SPICE-based models. Connections can be imported and exported to save time and offer flexibility. The result is a complete multi-board project suitable for advanced system-level analysis. This concludes the main portion of the presentation. Now we will finish it off with reasons why Hyperlinks has advantages over its competitors. Imagine a workflow where you manually pick nets of interest, crop or select a subset of the layout, define the ports, perform the meshing, and extract a model. This model then needs to be added to a test bench comprised of a driver and receiver models to form a final representation capable of delivering simulation results. This is a daunting task, even when considering only a small sample of nets. Which nets do you choose? How do you know you have chosen the worst-case examples? Now imagine trying to accomplish this workflow on an entire interface, verify complex signal, power integrity requirements, and achieve full timing closure. The point is, this is time-consuming, error-prone, and impractical for full interface-level analysis. So how would you solve the problem? With hyperlinks, you aren't bogged down with the manual aspect of extracting details of the interconnect. Net extraction is done automatically with the built-in field solver, including detailed via and transmission line models, coupling, and loss. Most other tools use manual extraction and analysis flow that limits practical post-layout analysis to a handful of signals. Automatic net extraction greatly simplifies the workflow, increasing the efficiency and allowing scalable verification. To demonstrate scalable verification, we performed post-layout DDR and SerDes verification on an Intel reference design. The design is a dual-socket server motherboard with 32 DIMM slots of DDR5 memory and 336 channels of PCI Gen 5. With the automated net extraction workflow that Hyperlinks offers, we are able to run full system-level verification using the DDRX batch and SerDes compliance wizards, complete with 3D extraction of 3D areas and parallelization through job distribution. Hyperlinks Power Integrity offers a complete, efficient, and integrated solution that offers tremendous value to the designer. The DC solution is extremely fast and efficient and allows the user to quickly assess voltage drop, via current density, max power density, and point-to-point resistances to ensure the design meets complex requirements. The AC decoupling wizard outperforms competitive solutions thanks to the new HyperPI solver, which significantly speeds up simulation performance while minimizing memory consumption. And modeling options such as lumped and distributed analysis yield flexibility. The PDN decoupling optimizer intelligently selects capacitors while working within your existing footprint constraints to optimize decoupling performance while minimizing the cost and eliminating unnecessary capacitors. When you simulate the entire interface, such as DDR and SerDes, there's a lot of data to report. Hyperlinks organizes and reports all of this data with expert visualization so you can answer the questions you care about the most: which signals passed, which signals failed, and by how much. Reports are presented in HTML format with summaries and hyperlinks to detailed data. You can also view critical waveforms and eye diagrams directly from the report. The report can be exported in a PDF format for archival and collaboration purposes. Hyperlinks offers unmatched integration and offers complete, proven workflows to maximize your design efficiency and reduce cost. Our proven workflows allow you to evaluate trade-offs and make critical design decisions early and often in the design phase while giving you confidence when verifying the design performance. Hyperlinks is fully integrated into Expedition Layout while offering seamless integration with other PCB design tools through standard design formats. Many of the workflows are automated, reducing setup complexity and manual effort necessary to get results. As shown earlier, the manual steps necessary with many other tools is impractical, especially when analyzing a full interface or even entire designs. And finally, are you looking for additional resources or opportunities to try Hyperlinks for yourself? Hyperlinks workshops get you up and running quickly by documenting complete workflows with detailed step-by-step instructions. Hyperlinks workshops are free and can be run virtually on the Accelerator Academy platform without the need for Hyperlinks software or licensing. Simply create a free account, redeem the Hyperlinks library of courses, and start learning today. Thanks for your time today, and remember, it's easier with Hyperlinks.